Welcome back, meteorology students. This is part one of our two-part series of our next lecture, which we're basically going to be over temperature and heat transfer. So first, this lecture, we're going to go over temperature scales, the forms of heat transfer, radiation laws, and satellite bands. So this one's got a little bit in it, but it's not too bad. Okay, so first, temperature. What is temperature? It is actually the measure of the average kinetic energy in a substance. So what that really means to you is how fast are these molecules moving? So you can see over here that warm air has quite a bit of motion going on in these molecules. This little trail behind it is supposed to kind of give you an idea of the speed here, and these are moving a lot slower. See how that little trail is just not that far, so they're going a lot slower in this cold air. So we know that in warmer air that the molecules move faster, and what we're doing when we're measuring temperature is actually, measuring how fast these molecules are moving. Pretty cool. We have three ways of actually measuring temperature. First, we have Fahrenheit. This is the one that most of us, have been born here or, brought up here in the United States because we use the Fahrenheit scale. We might be most, familiar with this one. Celsius, a lot of people from other places are very familiar with. Now, the Celsius scale is built around the freezing temperature of water. So if you notice that 0 degrees Celsius is going to be where water freezes, and where 100 degrees is actually where water boils. So Fahrenheit 32 degrees is where water freezes. This might be a test question for you. I do think it's important for you guys to know when water freezes, if nothing else, because when you move to other areas of the country, people are concerned about that 32 degree mark because when it hits that overnight, that's when we have to cover our plants. That's when we have to worry about black ice because that's when the water freezes and you might not know that, you're running over ice. But if you're aware of the fact that it's 32 degrees out, then you might be more cognizant or concerned about, oh, wow, okay, well, I need to slow down a little bit when I'm driving because I might hit black ice. And 212 in the Fahrenheit scale is when water boils. We do have a third scale of temperature, which is called Kelvin. This one is the one, most scientists will use. It's in a few equations that I've used in meteorology. I don't know if, commonly you'd hear, I don't think you've ever heard it on the news or anything like that. But, the Kelvin is built around the absolute zero. This is the theoretical temperature in which those molecules that we're measuring don't move at all. They just sit still. So they don't have any energy associated with them. So that's kind of where the Kelvin scale is built around. If you look over here, I do have kind of like the Kelvin, Celsius, and Fahrenheit scales right next to each other. Unfortunately, I don't think you can really build up too much intuition between the Fahrenheit and the Celsius scales because it's not a strict translation. It's not like, add 32 to whatever number here and then you'll get to Fahrenheit because the conversion is a little bit more complicated than that. There's some addition and subtraction to it. It's kind of a two-step thing where a lot of other conversions are just one step. But it does kind of give you an idea of, the boiling point of water, the highest temperature, which is here in California, Death Valley. I've actually been there. There's the largest thermometer in the world there. It's like, I don't know, 3 stories tall. It's this huge thermometer. It gets really hot there because it's in Death Valley. But it reached 134 degrees Fahrenheit. It's pretty hot. Body temperature here, we have 98.6, which is 37 degrees Celsius. We have freezing, which we said was at 32 and 0. And then we had the lowest temperature, which was also recorded in Antarctic here in Vostok in 1983 at a negative 129 degrees Fahrenheit. That is cold. I don't ever want to see that temperature in my life. I'm okay living in the Bay. The weather's really nice here. Okay, so heat actually is going to be energy, right? Because we have these molecules moving, and so basically it's going to be a measurement of that moving or that measurement of the energy. We can transform that energy from one object to another. We know this in our day-to-day lives. We know that if we were to grab, in this picture right here, a metal handle, if it's over a fire, that this would be hot and that we would burn ourselves and potentially drop the water and that would be kind of cool, not cool. But we know kind of some of this by our day-to-day life here. And I kind of like this drawing because it kind of shows you these 4 different methods. We do have the radiation. The heat is radiating, right? A lot of people know that term off of, oops, I didn't mean to do that. Off of, the fire. And then it is hitting the bottom of this pan, okay? And through conduction, it's going to basically warm up the bottom of the pan, and the bottom molecules of this water is going to start moving around and get excited and start moving faster. And then at that process, convection is going to happen when the water starts boiling. It's going to, or before it starts boiling, because it's going to rise to the top. And because this is this nice vertical motion here going on, it's transporting the heat from the bottom to the top of this boiling or warm water. So we do know some of these things by our day-to-day life. Advection we might not know as readily, but that's okay. We'll go over it here in a minute. Okay, and then there's one last one. There's kind of like 5 actually, and this one is actually latent heat. Latent means hidden, so just think of it as hidden heat. It's just hidden, something that you don't really think about. So basically, water vapor, already went over, is an invisible gas. Okay, it becomes visible when it changes into liquid, which is going to be, a process known as a phase change. Okay, changed phase from the vapor into the liquid form. Now, there's actually energy associated with that phase change. That energy is going to be latent heat. So a good definition here would be the heat energy, I'm trying to get my cursor, the heat energy required to change a substance, such as water, from one physical state to another. Okay, and like it says here, latent actually means hidden. Okay, so this explains why your skin feels cold when you step out of a warm shower. So you get out of a warm shower, and even if the room was the same, was warm, you'd still feel chilly, and that's because those little water droplets are actually evaporating off of your skin, and it has a cooling effect on your skin, which is great because that's actually how sweating works to cool us down. Because we sweat, and then we have water droplets on our skin, and it evaporates, and it kind of cools our skin down. So latent heat, is a very important thing. We're going to go back over this again when we come to, stability, when we come to thunderstorms, when we go into hurricanes, when we go into various different things here down the line in the semester. We're going to hit up latent heat over and over and over again. So what I want you to do right here and right now is just associate latent heat with phase changes. So if you hear in your head evaporation or condensation, think immediately hidden heat. There's some sort of hidden energy associated with that phase change. That'll help you out throughout the semester, I promise. Okay, so like I said, it's an important source of atmospheric energy. That would be why we go over it a few different times. Rising to high altitudes, vapor changes into liquid droplets and ice crystals. So we'll go over why, later on in the semester, but just understand that as, air rises, you're going to get some sort of change in phase, more than likely, depending on the temperature of the air up there. And when that happens, then you're going to get some sort of hidden heat associated with that, or cooling. And then heat is released into the environment. Now, I said or cooling because it depends on which direction we're going to. So evaporation is going to be where heat is lost into the environment. So heat lost means that it's cooling, right? When you have a loss of heat, then you're going to get colder. So evaporation actually has a cooling effect to the environment. Latent heat of condensation is where heat is given to the environment. So when you give heat to something, like a heater is giving you heat, then you're going to warm up. So condensation actually has a warming effect on the environment. Here's kind of a nice little depiction of that. You can see when things move in this direction, I can't point, but hopefully this is the right direction if you're looking at this. If it's going from, liquid to vapor, that's going to be evaporation. That's going to be heat energy taken from the environment. This heat energy taken means it's actually cooling, right? If you're subtracting heat, then it's going to be cooling. Now, on the flip side, if you go from vapor to liquid, then you're going to have condensation, where heat energy is released to the environment. If you have heat energy released in the environment, if it's adding heat, then it's going to get warmer. So just think heat taken. Go back to your, was that word problems? The word taken is like subtract sign, where it's heat released is going to be added. It's going to be more like a plus sign. And that goes from liquid to ice as well. Then it's going to be heat released, from ice to liquid, then heat energy taken. You can go directly from ice to vapor. It does not happen very often. But when it does, that process is called sublimation. And that's also going to be heat energy taken or a cooling effect. Okay. And when we go directly from vapor to ice, it's going to be called deposition. And that's where it's going to be released in the environment, or a warming effect. Okay. So just remember that there's definitely energy associated with these phase changes, and I can guarantee you I'm probably not going to test you on sublimation or deposition. 90% of the time, with weather at least, you'll see this having to do with from between the vapor and the liquid form. So that's what I would really focus on for sure, like understand that piece of it. We will see this over and over and over again. So I'm just telling you, memorize it, do whatever you need to do, that you'll need to know. Okay, so going back to those other forms, okay, we have conduction, which is where I was talking about, where the guy was holding the handle, we know from regular life, right? If we're poking a fire and we're camping and it'll get that hot, or like, I don't know if you've ever roasted marshmallows with like a metal tool, then it'll get hot on your hand, that kind of idea. It's why they put plastic on the outside, coatings on spoons and things like that. So we pretty much know that conduction is going to be, a way for heat to move from one substance to another. It's going to travel from hot to cold, and we know that air is a poor conductor, but metal is a good conductor. Convection is something you might not know as well, but this picture right here is going to be a picture of what convection looks like in our atmosphere. So the main thing to remember with convection is it's going to be a vertical transfer of heat. It's going to be vertical. Okay, see how this is like up and down? Okay, that cloud is kind of going like this upward motion. Okay, so that's going to be transport of heat from the bottom here closer to the surface aloft. So that's why they call that convection. Now, we talked about this, this mentions the convection circulation, which is where warm air expands and rises and then cools and sinks, and it creates this thermal cell. So here we can have, down at the surface, I keep trying to point to the screen like you can see me. So yeah, down here at the surface, it's heated up, by the sun. That warm air is going to rise, and then here a little bit later on, you can see it rising enough to where it kind of forms a little bubble, and then eventually it'll rise up enough to where it actually forms its own little thermal right here, its own little air pocket of air, that's going to be warmer than the surrounding air. By the way, the cool air will come down and replace the warm air. So because it's got to replace it, because it's displaced, right? If you have like even a liquid, think about a liquid. If a liquid is like moved up, then the more liquid will move down in order to fill in the gaps. Now we know, or we see different things being used for thermals in flight. I've seen many times birds using thermals actually to lift them up into the air, or just if you see them just kind of like soaring and not like flapping their wings or like actively moving, they're just riding on a thermal. They got one of these air bubbles here, right there, that they found, and they're just kind of hanging out right there. These guys, I think they're called paragliders, but these guys that are way more gutsy than I am because I'm afraid of heights. They actually find these thermals. I actually knew one when I was working at NASA, a guy that actually loved to do this, and he was telling me that he looked for specific cloud types because he looked for thermals in order to be able to paraglide. Hopefully I have that right. Okay. So we have convection, right, which is going to be that rising, that horizontal motion, but we also have advection, which is going to be a horizontal motion. So advection can carry properties of the air with it. So, right now we're talking about temperature, but it could be moisture as well. We have clouds forming because, we have this advection fog. We'll go over advection fog here later on the semester, but this transport of warmer air that's over the surface, and it goes over to the water, and the water is a colder surface, so it cools the air, and that's where that fog forms. But the point is that we have a advection going on because the air is moving horizontally and is changing temperature as it moves horizontally. Same thing when we have like fronts or things like that, circulations going on. We can have some sort of temperature advection going on, which is a horizontal motion to the air, and it might warm or cool depending on what environment it runs into. These are going to be the group questions that you guys can pause this video and see if you can answer them. I'm going to kind of keep moving though and assume that you paused it. Okay, so now here's where we move on to radiation. So we went over those other few kinds, and now we have radiation, which is the main way energy is transferred between the sun and Earth. Now, you might call them sun rays, the sunlight, you might call it lots of different things, but really it's radiation coming from the sun that we're receiving. And it's the transfer of energy by rapid oscillations of electromagnetic fields. That's a hefty thing to say, but basically what it means is that it's like transferring that energy, the motion of those molecules moving from one area to the next, or one substance to the next. The most important general characteristic is its wavelength, which is defined, this right here should have this inserted in there. I'm not sure why it's not there, but this is called a lambda. But it's wavelength, which is defined as crest to crest. So right from here to right here is going to be its wavelength. Now, you could do it from here to here as well. You could do any one of these as long as you're finding, the next one. But that whole idea of how much space there is between, the full oscillation is going to be the wavelength. And then radiation travels through at the speed of light, right? We have solar radiation, which is going to be visible when we see it, which is 186,000 miles per second. So it's moving pretty fast. Okay, so each beam of incoming sunlight can be either reflected back into space, and the percentage of sunlight that's reflected back into space is considered our albedo. And things like snow versus dirt versus ice, versus whatever, like water, different things or things on the ground, whatever it hits is gonna have a different percentage that it bounces off of. So different materials have different albedos, but that's what that's considered. It can also be reflected by clouds or, be absorbed by clouds, the atmosphere, or the surface. So these are things it could be reflective off of, but it can also be absorbed. It can also be absorbed by clouds. It can also be absorbed by different chemicals in the atmosphere, like greenhouse gases. So either it's going to be absorbed or it's going to be reflected. And things that are absorbing are actually going to be warmed by that absorption. And things that are reflected are going to have a warming. They'll probably have a cooling effect, actually. So as the wavelength increases, the energy carried per wave increases. Oops, okay. So as you see here, the wavelength of an AM radio wave, okay, is going to be really small comparatively to an X-ray, which has a really short wavelength, but is going to have a lot of energy, right? If you get in the middle of an X-ray, you could be fried. But AM radio waves are going around all the time, and that doesn't bother us at all. Visible light also wouldn't bother us. Let's see, UV waves, those aren't good for us either. But it kind of, you can see here how more energy is actually associated with it with shorter wavelengths. And we'll get into that here in a minute. Okay, so energy is going to come from the sun through space in the atmosphere in the forms of waves. Okay, this is called radiation. But the main thing to remember here is going to be shortwave radiation. Okay, so all objects at the temperature greater than 0 Kelvin, absolute zero, emit some type of radiation. So what that means is I emit radiation, you emit radiation. This table emits radiation, my computer emits radiation. But then it also is going to emit long wave radiation. So we have the solar radiation, which is shortwave coming in. It's going to hit this is supposed to be the planet here. And so like Earth. And so it's going to hit the planet Earth. Okay. And then the part of it that's reflected off of the Earth is going to be reflected in the form of long wave radiation. Okay, like we said, all objects emit radiation, and the sun emits radiation mostly at shorter wavelengths in the UV and visible, and the Earth emits radiation mostly at longer wavelengths in the infrared, which is warming. Okay, so what that actually means is that we're warmed from the ground. We're not warm from above, we're actually warm from below. So the sun comes down with the shorter wavelength and UV and visible wavelength. It's going to hit the ground, it's going to change wavelength into the shorter or longer wavelength, which is infrared, and that's going to be the warmth, and it's going to come back up. And there's going to be a difference depending on the temperature of the emitting body. So, different bodies will actually emit at different wavelengths. It's basically telling the same thing. So this brings us to a couple of radiation laws. Okay, I'm not going to get too technical with you. I feel like that's kind of a little bit more for meteorology students. But remember here that warmer objects emit more radiation than colder objects. This kind of makes a little bit of sense, right? Because if, the sun is going to emit more radiation or more power or more energy than the Earth does or the moon does or any other planet does. The sun, is going to emit a lot more energy than anything else. Okay, and that's the Stefan-Boltzmann law that's basically saying that. The other thing is that warmer objects like the sun emit a higher proportion of their energy at shorter wavelengths than colder objects. You can see right here, this is going to be our shortwave radiation. So this is the sun, 6,000 degrees Kelvin. You can see how most of the radiation that it emits is within the visible spectrum, which is a short wavelength. And then you can see the Earth at 288 degrees Kelvin. It's going to be a lot less. This long wave radiation is going to be between 5 and 30 micrometers. And so this is going to be, I'm going to say, a lot longer of a wavelength. So that's basically the takeaway of this. I'm not going to get too bogged down into this at this point. So just remember, warmer objects emit at a higher proportion. Warmer objects emit at a shorter wavelength and more energy, which would be both laws. Okay. Now, we went over all of this wavelength stuff and radiation and all that, but this is the point where I kind of like to go into, this is how satellites work. Satellites actually are looking for, for what the Earth, like what temperature, is it actually like emitting from it? And so it actually measures it, and that's how the satellite works. But there's actually 3 different bands. So this band right here, this is actually a measure of the visible light. You can tell that because it's dark over here and it's light over here. Well, the sun rises and sets in the east before the west, right? So the sun basically set over here, and it's still over here it's still up. So this is going to be more like a picture. It's just going to be measuring how much of that visible light is coming off of the Earth. Which is great because you can see like clouds and you can see all sorts of different things, inside of this picture here. They can look at the movement of clouds and the structure of clouds. When I'm storm chasing, I look for, cumulonimbus, like storm clouds. I don't see any right here. They're too apparent, maybe over there, but that's what we're looking for. So different scientists actually use different, they're studying different types of clouds, can look at this band to kind of have a quick snapshot. Now, this one's going to be measuring infrared, like I said, the temperature. And we do know that, the higher up the cloud, the colder it is. So, we can tell what type of cloud these actually are based upon its temperature. We can also tell, I'm trying to think. If it's snow on the ground versus if it's a cloud. Lots of different things. Smoke, that kind of thing we can tell. Because sometimes when you're looking at the visible imagery, it's not as apparent as if you're looking at snow or smoke than if you're looking at clouds, where you can look at this and know kind of immediately. And then this one's also going to be looking at a different wavelength. in the water vapors in the 6.7 to 7.3 micrometer wavelength. So this is going to be a measure of how much water vapor is actually in the air. So this area like right here is going to be really dry. This area will be really dry, and these are going to be some areas of moisture. But you can actually look at like large scale type of motions that are going on by the water vapor. It's kind of cool when you like put it in motion. You can see like different waves kind of going through and stuff like that. All right, so here's the second set of group questions. This is the end of this video. So we only have one other video left after this one. I hope you guys are having a great day.